Greetings, physicists. This video will be about rolling objects, rolling motion, rolling without slipping, and then also energy associated with objects that are rotating. So we'll start with rolling motion. So we'll take an object, and I'm going to define, or let's talk about three ways to think about this. You have an object that just moves this way and slides across the ground without rotating. We would call this translational motion. And like I could draw the dots like this. And then when it gets over to here, the dots are all still in the same place. It's still moving sideways. That's translational motion. You could have an object that sits in place and just spins and doesn't actually move side to side. And this would be rotation. And then you have an object, I can't draw circles to save my life, that does one of these and it moves to here, right, and back. So it's spinning as it goes, but it's also moving forward, and it's not sliding, not slipping across the ground. This would be rolling. So rolling has both. It has some translational motion because the object does go side to side, and it has rotation because the object is spinning as it goes, and we're combining these two types of motion. So here's how you combine them. If we were to draw vectors, velocity vectors for this object up here, every single point on the object has a velocity vector forward. The bottom has a velocity vector forward, the top has a velocity vector forward, etc. If we were to do that for the rotation, I drew the angular velocity, but there is a linear velocity associated with any of these particles. As this thing rotates around, when you get to the top, that particle, that individual particle, has an instantaneous velocity that is tangent to the top. And when he gets down to the bottom here, he has an instantaneous velocity that's tangent to the back. So what happens if we take these vectors and superimpose them on top of these vectors for the rolling motion? Well, you can see that on top, this vector is going forward, this vector is going forward, so I should get a bigger vector on top. If we look at the sideways stuff here, these vectors are down or up, or the middle is not moving. So the middle will not change here. In other words, if this vector was going forward, this vector will also be going forward. But it doesn't get as much, it doesn't get a boost. So the top vector gets a boost, the middle vector doesn't get a boost. The bottom vector is going backwards, and the top vector, and of the translational motion, that vector is going forward, so this would come to a stop. So in pure rolling without slipping, the very bottom here has a v equal to 0. The very middle has the same velocity as the translational dude, so this is just v. And then the very top has like a 2v. He's going twice as fast because he has his rotational motion plus his translational motion. So that's an interesting thing. And you may I was going to say you may have noticed this if you ever rode a Ferris wheel, but that would only be true if the Ferris wheel broke off and then rolled down the road, that at the very bottom you would feel like you were stopping, and at the very top you would be going twice as fast. Wouldn't that be a trip? But for that reason, rolling motions tend to do this. They tend to go, if you're on the outside edge of that wheel, that's what you're feeling. You go fast at the top, and then you go, no, you're not going anywhere when your part gets to the bottom, and then you go fast as you accelerate stuff. Okay. So another interesting point, and we had mentioned this, I may have mentioned this briefly in the friction chapter, but if you're in a car, and we'll focus on the wheels of the car, traveling across the pavement, and the car is going like this, when the point of your tire that is impacting the road gets to the bottom, it stops moving while it's down there. While it's at the bottom of the wheel, it doesn't have any velocity, any relative velocity to the ground. And when it's at the top, of course, it's going very fast, and then it gets back to the bottom, it stops again. And your car doesn't skid across the ground, so it's not sliding over the ground. So the friction force between your car's tires and the ground is actually a static friction. How about that? That's kind of a trippy thing when I first heard it. Okay, so that's rolling motion. And let's also talk about kinetic energy. Because when we solve rolling motion problems, they almost always involve solving kinetic energy equations. So we have an object spinning. Let's just take an object that's spinning right now, not one that's actually rolling yet. But it's spinning in place, a disk around an axis. If you were to take a point on the outer edge, it has some, at some instant, and you took a snapshot, right at that instant, that point would have an instantaneous linear velocity or tangential velocity. But we can also convert that to an omega, right? Because v was equal to r omega. So it also has an angular velocity equal to, r omega, or an angular velocity equal to v over r. So if we write it at this point, since it has a velocity, it also has a kinetic energy. It has a kinetic energy equal to half mv squared. That's the kinetic energy that it has. It's based on its instantaneous linear movement. Okay, we're not going to say that there's a different kinetic energy that it has because it's spinning. It's all linear kinetic energy, and because kinetic energy doesn't care about direction because we're squaring that velocity, it can point any direction it wants. So when it's over here, as long as that's a constant velocity, then it still has that amount of kinetic energy. Okay? Well, let's say I want to replace that v with r omega. That's the same as saying 1/2 of m times, instead of v, I'll do r omega, and I'll square that. So that's 1/2 m r squared omega squared. Well, you've seen this term before. That's moment of inertia. At least for a point particle, that's moment of inertia. So the kinetic energy of an object will be of a rotating object. You can calculate it using 1/2 mv squared for its instantaneous tangential velocity, or you can use 1/2 I omega squared. And look how that perfectly lines up, right? Because mass and I is essentially the angular version of mass, and for v, omega is the angular version of velocity. So you can use this equation, this kinetic energy equation, to solve problems that involve spinning objects and not have to think too hard about it because it looks like the exact same equation just replaced with angular components. Okay? So a typical rolling problem we have an object, let's say this is a solid disk of mass m and radius r, and it's moving this way with a linear speed v, and it's rotating with an angular speed omega as it goes forward because it's also rolling. Well, we can then say that it has the following energy. Its mechanical energy, its total mechanical energy, will be equal to 1/2 m times the linear velocity squared plus 1/2 m times the omega squared. Not m, excuse me. 1/2 I omega squared. And then we would be able to solve problems like this. It's also interesting to note that because the bottom point of this rotating object, this wheel, is not moving, we very often consider that to be the pivot point. So if there was an angled problem, this comes in. Oops. This comes in when you have like a wheel rolling down a hill, and it's going this way. And if you remember from sliding objects in kinematics, right? This hill was at some angle theta. There was an acceleration down the hill equal to g sine theta. And there was a force down the hill. The component force of gravity down the hill was equal to mg sine theta. Well, now that force is causing a torque, right? If this object is not just sliding down the hill, but is rolling down the hill, then you have a torque equal to some force. Well, let me write this correctly so we don't get in the bad habits. We get a force equal to an r cross f, and we have the radius, right? The radius is just, let's say the radius is there, so we have whatever radius that disk is at times the force. Well, the force is mg sine theta. And we can say that because the force of gravity acts on the object's center of mass, but the distance from the center of mass to the place where it's pivoting, which is the ground, is 1 radius. So keep that in mind when you're dealing with rolling problems. Is the downward edge of that wheel is considered to be the pivot point. Okay, that's the lecture on rolling motion and rotational kinetic energy.